So far we've looked at the quantities that describe motion. We then looked at Newton's laws of motion and how force ties in. And finally we've also looked at energy as well. The next quantity that we need to look at now is momentum. Now momentum, it's a bit of an unusual one in that it's the definition is a little bit strange, I think, in terms of physics quantities. So momentum is simply the quantity of an object that's given by the product of the object's velocity and mass. So usually we talk about a rate of change or a measurement, or in this case it's simply the product of mass and velocity. So the equation then is pretty straightforward. So the symbol we use for momentum is P, and it's simply then the product of mass and velocity. So that particular equation is an important one to be familiar with. So literally the definition of momentum is just the equation that you use to calculate momentum. So it's not as easy a quantity to relate to, because it's simply just that product. A couple of points to note about that quantity of momentum. Because velocity is a vector quantity and we're just multiplying it by the scalar of mass, that means that momentum is a vector quantity as well. So it's important to note here that direction is important. It's also important to note that we wouldn't talk about momentum as being mass times speed, so it's always mass times velocity. The units of momentum we get by simply multiplying the units of mass and velocity. So the units of mass are kilograms and the units of velocity are meters per second. So the units of momentum are kilogram meters per second. So again, it's a bit of an unusual one. If you said that something had momentum of 5 kilogram meters per second, it's not an easy quantity to draw to mind as to what that actually relates to or what that actually is. To give you a bit of an example though, imagine we have a truck that's relatively heavy and has a mass of 2,400 kilograms. And that truck is moving along with a velocity of 5 meters per second to the right. We could then calculate the momentum, very straightforward calculation here, mass times velocity. So the mass being 2,400 and the velocity being 5 meters per second to the right would give us a momentum of 1.2 by 10 to the 4 kilogram meters per second. So you can see it's a fairly easy quantity to calculate. Now I'll just mention here as well, let's say we had a car that was half as big, so a car that was only 1,200 kilograms moving at the same speed, same velocity, sorry, then obviously then the momentum will be half as great. If this truck was moving twice as fast, at say 10 meters per second, then the momentum would be twice as great. So momentum here is just in and of itself, it's not a particularly useful quantity. Yes, we can compare it to different scenarios where the mass might be greater or the speed might be small, whatever that might be. It's in and of itself, it's not really just momentum that we need to look at. There are other quantities that we need to consider. So if we then consider those different changes, have a look at a few of those effects. So it follows logically then that the momentum of an object it's going to change if we get a change in its mass. So as we said, if the mass is twice as big, then the momentum will be twice as great. Or if its velocity changes. So it's a fairly obvious statement, but one that we need to look at in order to make a few links to other things as well. So if we look at that second point of its velocity changing, if velocity changes, then what we're really dealing with is an acceleration. So if we have acceleration, we're basically then saying that for an object to accelerate, or for the velocity of an object to change, we know from our understanding of Newton's laws of motion, an unbalanced force must be acting on the object. So you can see there that there's a link to Newton's second law. We'll develop that a bit further in coming videos, but just wanted to draw your attention to it now as something to think about, something to keep in mind as we consider these ideas associated with momentum. Now, the concept of momentum, like I said, in and of itself, it's not particularly helpful. So it's more about looking at how momentum is involved in a few different scenarios. And the main one that we're going to look at is so the concept of momentum there. It's the underlying principle involved with collisions. So what do I mean by that? Basically, any time we have a collision, so any two objects interacting, exerting forces on each other, we have a principle of conservation of momentum. Now, we've seen a few different scenarios where we have a law of conservation. This is now a law of conservation of momentum, and what that means is that if we write it another way, the total momentum of a system, so if we're in talking about a system, let's say we're dealing with two masses that are colliding, the total momentum of the system before a collision is the same as after, or is equal to the total momentum after. To put that into context, let's have a look at an example. Note that this is only one specific scenario. There's going to be lots of different scenarios that would affect the way that you go through and analyse this sort of situation. Imagine that we've got two masses, m1 and m2. m1 is moving to the right with some velocity u1, and m2 is moving to the left with some velocity u2. Note that these masses and velocities aren't necessarily the same. So that would be the initial condition, so the before. Then after the collision, we have them bouncing off each other, so that m1's now moving away with a velocity v1, and m2 is moving in the opposite direction with a velocity of v2, so something along those lines. Now, if we look at what happens before and after, we can say that the total momentum beforehand, so if we call that pi, is going to be equal to the total momentum after, which would be pf. But we can break those down into separate momentum. So we've got two objects to begin with, so that would be p1i plus p2i, and that would be then equal to p1f plus p2f. So we're sort of drilling down into the individual objects. Taking that even further, we know that the initial momentum would be m1u1 plus m2u2, and the final momentum would then be m1v1 plus m2v2. Now that's a very generic sort of equation, and not one that's necessarily always going to apply. So in this situation above, they both had initial velocities, and they both had final velocities. If one of them was stationary, so let's say that object 2 was stationary, then this term here would completely disappear because u2 would be equal to 0. So rather than talk specifically about this is a representative equation, we can summarize it more generally and basically say that we're looking for this sum of the initial momentum of all of the objects and this sum of the final momentum of all of the objects. So we can use that expression to simplify this scenario, and that's the one that you'll find in the data booklet. In the next video we'll look at conservation of momentum in specific situations and take that a little bit further.